Okay, let's continue our discussion in chapter 9. In the previous video, we talked about the from a table, how do we determine when two attributes are related or not. However, we have to realize that even for two things that are completely independent, just because of sampling fluctuations, it's normal for you to observe the ratio between the variables in different rows or different columns are slightly different. So how different is different enough for us to conclude an independence or dependence? Well, we have to introduce some more scientific method to make a determination. For example, here in this example, the vitamin C example, if you look at the first table, which is what we observe, and versus the second table, which is what we would expect theoretically, assuming that there is no connection, or in other words, assuming independence between vitamin C and catechol coda or not, you see these two tables are very different. And we might be inclined to say that these two attributes are dependent, or in other words, taking vitamin C will help to prevent the cold. However, is it different enough for us to make this conclusion? And the answer is we'll introduce what is called the chi-square test. The chi is actually the Greek letter, which is kind of looks like an X. It's pronounced as chi. And for each table, we look at these two tables, and one is what you actually observe. Another one is what you would expect, assuming the independence. So you put these two tables side by side. And then for each of the cell, for example, if you look at the first cell, what we observe is 104, and what we expect, assuming independence, is 88. So you do the subtraction, you observe the minus what you expect, and then you square the difference, use that as the numerator, and then divide by what you expect. So in this particular case, and the first cell, for the first cell, I'm going to use the whiteboard. And so here. So actually move this. It might be easier to move this to the left. This is the whiteboard. Okay, cool. All right. So now let's consider the difference between these two tables by, first of all, we use the first cell, which is 104, and then minus 88. This is what we observe minus what we expect, and we square the difference. And now we divide it by what we expect. So assuming independence, so we divide by 88. So this is the first cell. And now the chi-square is calculated by doing this to all the cells. So the next one is 72 minus 88. And then we square it. And then we divide by 88. And then plus the third one is 296 minus 312. And then you square it, you divide by 312. And finally, you have 328 minus 312, square it, and then divide by 312. And you can use a calculator or R to find out this value. Of course, at the end of the day, you just get some number, and this number itself does not tell you directly whether they are dependent or independent. Skip the details, and you would get a number which is approximately 7.46. Now we need to go to the back of the book, and if you go to the page, if you go to the appendix of the book and page 550, let's see. It's actually 543. So look at the table A-3. So here's the table A-3 on page 543 of your book. And Now, for this particular question, the degree of freedom and is 1. I'll explain this. And why is 1 is because it's 2 by 2 table. And assuming you know the totals, and once you know one of the values and one of the cell entries, then you can use the subtraction to figure out the rest. So the degree of freedom is 1. Or in other words, you look at the first row of the table. You look at the first row of the table. So here, the first row of the table will look roughly like this. Up. And the first row is degree of freedom 1, and you see some numbers such as 0.99 and 0.95 and 0.990 and 0.5 and also 0. You see 0.2 and 0.1 and 0.05, 0.01, and also 0.001. So you see all those numbers. And now for the degree of freedom in the first row, you see some numbers such as 0. I use another color, so it's 0.00, so it's 0.00, and 0.02, and also 0.45, and also 1.64, and 2.71, and 3.84, and now is the 6.63, and also 10.83, so 10.83. Well, here, what you observe is this chi-squared value, 7.48, 46 is between these two values. Okay, it's between these two values. So from the table, the p-value, which corresponds to the probability level. So here is the probability level. Or sometimes called p-value. So the p-value, the corresponding p-value is between 0.01 and 0.00. So this is the probability p-value we find. And usually a rule of thumb is whenever this probability of p-value is less than the threshold of 0.05, so it's less than this threshold. And I'll show you the next slide. When the p-value is less than 0.05, we conclude that there is a significant association, or in other words, they are dependent. Again, the small p-value, p less than 0.05 would mean dependent, and p greater than or equal to 0.05 would mean independent. So in this particular case, we get a chi-squared value, which is very small. It's actually less than 0.01. Although from the table, we don't know the exact values are. I will show you how to do this in R in just a minute. But for now, you just need to realize that here now the p-value is less than 0.01. And therefore, we have strong evidence to support the connection between taking vitamin C and not getting the code. And in fact, we can do the R test here and chi-square test in R here. And so you can copy and paste the code. And again, in this course, I'm not expecting anyone to compose this code just by yourself, but as long as you know how to copy and paste it. And then you can see here, the chi-square value is 7.45, which is approximately the same as what we did before. And df means the degree of freedom, and it's 1 because it's 2 by 2 table. And also we know the p-value is 0.006311, well, which we don't know yet by just looking at the book, because we only know the p-value is between 0.01 and 0.001. Now we have a more precise p-value. But in any case, the conclusion is clear, and that these two attributes, taking vitamin C versus getting a code or not, are dependent. In this course, you're welcome to do the chi-square test by hand, but I would recommend doing this in R. That'll make things much easier. So there's another example. So there are two races of amoebas, and basically some kind of bacteria, and I've always have hard time pronouncing the names, but basically there are just two types. One is called a small one is called a large one. And now we would like to find whether the absence or the presence of the small one has anything to do with the absence or the presence of the large one. So here, this is the data. And now what you can do is to do the chi-squared test just by using this table. And again, I'm going to skip the doing things by hand part. So what you can do is with the R code is just to copy and paste the old R code, just modify the numbers. So here you can change this to 12 and then 35. Remember here we'll do it one column at a time, and then 23 and then 68. So this is the modified numbers. And then the dimension names, well, this is really just optional. And if you want to type in the dimension name, just make the table looks nicer, you're welcome to. Otherwise, you can just skip it and then just do the chi-square test without worrying about the dimension names. So you see here, now you have the table data, always double check if this table data is the same as the one given here. And now you're going to do the chi-square test. The chi-square value is actually very small. It's 0.001083, and the degree of freedom is 1, again, because it's 2 by 2 table. And now the p-value we find is 0.9737. So this is a very large p-value. Remember, we mentioned earlier that larger p-values, which means larger than 0.05, would indicate that there is no significant association between the two variables. Or in other words, in this particular case, we would conclude that the absence or the presence of the big type will have nothing to do with the small type. So if a doctor tells you, hey, you're likely to have the small type just because you have large type, the answer is no, because those two are not connected to each other. All right, great. There's another example, error accidents, and I would encourage you to come back to this example after we do the next example. So don't worry about this for now. We'll come back. Well, you can come back to this and do the chi-square test. And for the larger tables, remember the degree of freedom is equal to R minus 1 times C minus 1. Just reduce the number of columns by 1 times the number of rows reduced by 1. So now, in the last example, the occupation and aptitude, we divided people into different occupations, and then we collect the data, and based on their aptitude and measure during the training and occupation. So we get some table data like this. This is, of course, we divided occupation into 3 or 4 categories, O1, O2, O3, O4. And then we look at aptitude, which is A1, A2, A3, A4, A5. And then we ask the question, is the aptitude connected to occupation or not? Well, the answer is we can do the chi-square test. In this case, I'll just use this table data and use this copy and paste this into R, and R will automatically do the chi-square test for me. So in this case, the chi-square value is 35. The degree of freedom is 12. Think about why. Well, here is the reason. Because in this table, we have, see how many rows? 1, 2, 3, 4, 5 rows and 4 columns. So again, remember, reduce the row number by 1, so you get 4. Reduce the column number by 1, you get 3. 4 times 3 is 12. So that's the degree of freedom. Now you have a p-value, which is really small. Now I want you to pause the video and answer the question. Does this suggest there are independence between the aptitude and occupation, or does this suggest a connection? Or I hope you thought about this. And the answer is a small p-value. Small p-value indicates the dependence. So here, if you have a very small p-value, which is less than 0.05, that implies that occupation is dependent on the aptitude. And you can do this in R. Now I encourage you to go back to the previous example, which we skipped, the error accidents. And then this is the observed, this is the expected. When you do the chi-squared test in R, and you only look at the observed, don't worry about the expected, okay? But if you want to do it by hand, of course, you will need both. So I would encourage you to use this. In R, you need to modify our code. I would let you think about how to do it. You need to modify these numbers, and also the number of row would be equal to 2 instead of 5. And of course, the dimension names will be optional. You don't have to worry about it. And then I would encourage you to do the chi-square test, and then get your own conclusion, and then see if that agrees with the conclusion you can find in your book. All right, that finishes the long chapter 9. I wish you all the best. I'll see you in the next chapter.